Hi, my name's Dave, and I've been asked to speak to you all a few minutes today about epidemiology. I know that's something you've been studying the last few days, and maybe you have a few more days to think about it. And I was asked to talk about epidemiology in reference to climate change. That's a pretty interesting combination of factors, so that's what we're going to try to do. So we're going to talk about epidemiology, climate change, and I'm actually going to try to make this stuff interesting. We'll see how I succeed at that. I think it's very interesting. Let's see if I can make it interesting to you. So before I prepared a little bit for this talk, I decided to go out and take a look at your website, the charter school that you're in, for science and math, and that's really pretty cool. And what I learned is that every one of you who's listening to this and everybody at your school actually volunteered to go there. You signed up and applied to be a student at this school. And that tells me that you're going to be more in tune to science than the average bear. You're probably going to be more in tune to math than the average bear. And you're probably going to like this stuff a little bit more than the average bear. So I'm really encouraged by that. I even looked at your charter. I'm not sure all of you maybe have done that, but your charter makes a couple of statements, and I'm going to read them. It says, this school will work to develop students who can think, not just memorize, and who can figure things out using their minds and their hands, not just take a test. It goes on to say that this school will develop higher level thinking skills and will engage in meaningful classroom dialogue. That's really good stuff. And we're going to talk about getting the facts straight. I love the fact that this school is oriented just for this purpose primarily. So we're going to talk a little bit about how you arrive at truth and how you arrive at things that you commit to believe for the rest of your life. And we're going to talk about that just in a minute. So what is epidemiology? It's a branch of medicine. It deals with the incidence, distribution, and possible control of diseases and other factors relating to health. And what is climate change? It's a change in global or regional climate patterns, in particular a change apparent from the mid to the late 20th century onwards, and attributed largely to increased levels of atmospheric carbon dioxide produced by the use of fossil fuels. Another definition goes on to say, some people call it global warming, and it refers to the rise in average surface temperatures on Earth. And importantly, an overwhelming scientific consensus maintains that climate change is due primarily to the human use of fossil fuels, which release carbon dioxide and other greenhouse gases into the air. Now naturally I can't see you because this is, after all, a video. But if I could, I would ask you for a show of hands of those of you who are listening to this who believe that climate change is real. And I'm assuming that most hands went up. And for those who did raise their hand, I would ask, how many of you believe that it's caused by human activities primarily? And I'm assuming most all the hands went up, but I'm guessing a few maybe didn't. And then I would say, for those of you who don't believe climate change is real, why don't you believe it, and where do you get your information? And for those of you who believe it's real but don't believe it's caused by human activities, what do you think is causing it? I keep hearing arguments about solar patterns and all that, but we're going to talk about that. So if you haven't already learned, I'm going to talk to you now how we should arrive at truth, and so you can make up your mind about these important things in a way that's rational. And there's three ways I want to talk to you about it. First is something called critical thinking. And my guess is you've been introduced to that term already by some of your teachers. The second thing is the scientific method. There's that good old scientific method again, as maybe the best and perhaps only way to arrive at the closest thing to truth in our physical world. And in the reference to climate change, I'm going to talk about a third way to arrive at truth, and that's something called the Intergovernmental Panel on Climate Change, the IPCC, and I'm guessing you've heard of that. Critical thinking means making reasoned judgments. Basically, it's using criteria to judge the quality of something. In essence, critical thinking is a disciplined manner of thought that a person uses to assess the validity of something, a statement, a news story, an argument, or research. So one rule of critical thinking that I've deduced on my own is that when someone makes a statement that's an important statement about an important topic, you have to consider that statement in light of where that person gets their money. So let me give you an example of that from a chapter in this book that I'm writing about climate change. I'm just going to read a couple of sentences for you. I read a report in The Guardian UK, which is a journal, in June of 2011 about a prominent scientific researcher, Dr. Willie Soon, who is perhaps the most well-known climate skeptic. He's an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, and he's argued that solar variation alone is the reason that the Arctic is melting. And he has also maintained that polar bears are not at risk from the changes in the Arctic. That's pretty compelling coming from someone with his credentials, especially if you're in the camp that human activities are not responsible for climate change. But this Guardian story went on to say that records just disclosed indicate that since 2001, Dr. Soon has gotten $1 million from the fossil fuel industry, including Koch Industries, ExxonMobil, the American Petroleum Institute, and the Electric Power Research Institute. Dr. Soon argues that this money has not influenced his reports, but what is a reasonable person to think? What do you think of after hearing this statement in the article? So that's an example of how critical thinking has to be applied. You need to remember these things. You've got to be careful and not jump to a bunch of conclusions. The second thing that we do to get truth in this universe is the scientific method. And I'm sure all of you have been introduced to the scientific method by now. It's a method of procedure that's characterized natural science since the 17th century. It consists of systematic observation, measurement, and experiment, and the formulation, testing, and modification of hypotheses. So in other words, somebody makes an observation, something happened, and they say, I wonder why that happened. And they say, gosh, it could be this or that. I think I'm going to design an experiment and test and see if this variable that I believe is causing this actually causes it. You have to be careful to control all the other moving parts so that the only one that changes is your variable so that the conclusions are caused by it. And then a very critical part of that is at the end, if you found some new information and moved the body of knowledge forward, in science especially, you have to publish that information in a peer-reviewed journal. And these journals are very difficult to get your papers published in the first place. So they have their own panel and they scrutinize what you wrote. So there's the first hurdle. And then the really scary part, once you publish it, every other scientist who reads it, who has anything or knows anything about your field is going to say, I'm not sure that sounds right. I'm going to see if I can read the paper and replicate their results. Can you imagine publishing something that's new and not being really sure about it, even if you get it by the peer-reviewed panel at the magazine? Now you've got every other scientist in the world see if they can overturn your results. Guess what happens to your career if you publish something and it turns out not to be correct or you can't replicate the results? In 1989, at the University of Utah, there were two professors, a Dr. Fleischman and a Dr. Pons. And they were doing an experiment using liquids in a laboratory in a beaker, and they were combining some chemicals with heavy water, and they were hoping to create fusion. And of course you know that fusion is that process in nature where more energy comes out of the process than went into it. And remarkably, they believed that they had put the right combination of chemicals together, and they actually believed that they got more heat out of the reaction than the energy was that went into it. And they published that, and they got it published in a peer-reviewed journal. And guess what? Nobody could replicate their work. It just couldn't be done. And of course they were shunned, and they were their reputations are pretty much ruined, and it added a lot of shame at the University of Utah. The point I'm making is scientific method is that process that has the greatest chance of getting right answers and of being right for all the right reasons. If you look at climate change, the conclusions that have been reached and are being reached are all based on the scientific method. There are people in Congress who say you can't trust science anymore. Really? What are you going to trust? Somebody's biases? The scientific method has been proven over and over and over again, and occasionally they will find errors, they will find mistakes. So the progress that's made is a sort of a jagged line up to the right as we increase the common body of knowledge. Once in a while there's a correction. And this scientific method is the process that gave us powered air flight, internal combustion engines, vaccines against deadly diseases, deduced the DNA double helix, gave us nylon rayon, Teflon for your fry pan so your eggs don't stick. All the technological advances that we enjoy came about because of the scientific method. Why would the scientific method be good for all of that and somehow be flawed when it comes to climate change? Well, guess what? It wouldn't. And now when we're talking about what is known, especially about climate change, I want to talk about the Intergovernmental Panel on Climate Change. This is an agency that was formed by the United Nations in 1988, and from 1988 until 2014, it has issued 5 reports. And the most recent one, of course, last year, and it comes out usually in 3 parts, 3 working groups. And it basically takes everything that's written and published, peer-reviewed articles, synthesizes them, and reaches conclusions. Let me read you one thing it said, and I'm going to read you a little bit more in a minute. It says, this body includes more than 1,300 scientists from the United States and other countries and forecasts a temperature rise of 2.5 to 10 degrees Fahrenheit over the next century. Now I'm going to give you more of their conclusions in a minute. Now I'm going to digress just a second, and I'm going to bring up a new term. In this talk, I'm guessing that a lot of you will know what this term is. It's called paradigm. What is a paradigm? Well, a paradigm is a framework containing the basic assumptions, ways of thinking, and methodology that are commonly accepted by members of communities or groups or disciplines. So what has been the commercial paradigm operating in the developed world in the last couple hundred years? It goes something like this, starting with the Industrial Revolution in 1781 when James Watt patented the first practical steam engine. Here's how the paradigm got created, and here's what we've still been living with. 1, we can build machines to do our physical work. Can you imagine the back-breaking manual labor that humans have always done? Happy day, we can do machines that'll do that work for us. The machines require a source of energy. Okay, no big surprise. The earth provides limitless, cheap energy in the form of oil, gas, and coal. There seems to be no downside to burning all of this fuel for energy. Now think about that a minute. We can build machines to do our work. The machines require energy to run. We have this almost limitless supply of energy, and there seems to be no downside. Guess what? That last part of the paradigm was always wrong. It was just that the earth was so massive, the atmosphere, the oceans, we just didn't imagine that we were filling it up with something that seemed harmless, carbon dioxide, and now more than ever methane. We just didn't know that it could be causing a problem. And also, we now know that the pollution we're putting into the air is something we're going to have to fix, and we're going to need to fix it sooner than later. So that paradigm that we're operating under has to change. When did we start noticing climate change? In 1859, there was a scientist whose last name is Tyndall, and he discovered that some gases block infrared radiation. Well, what's another word for infrared radiation? Heat. So in other words, when the light from the sun comes in and strikes the earth, it comes right through the atmosphere. It strikes the planet Earth, and in dark surfaces especially, it heats it. Then when the heat builds up, the heat starts radiating back from the Earth, and it's no longer light, it's a part of the spectrum you can't see. It's long wavelength radiation known as infrared, and better known as heat. Well, guess what? Scientists discovered that the CO2 molecule keeps that heat radiation from getting past. It blocks it. So it didn't take a genius really to figure out that if you put enough CO2 into the atmosphere and the heat started building up, that heat's going to be trapped below that layer of CO2, and that's what we've been doing. In 1896, which was 119 years ago, a Swedish scientist named Svante Arrhenius published the first calculation of global warming from human emissions of CO2. 119 years ago. This is settled science. The phenomenon of CO2 blocking long wavelength radiation is settled science. If I ask you, at what temperature does water begin to freeze? You'd say, well, that's easy. It's 32 degrees Fahrenheit or 0 degrees Celsius. And if I ask you at what temperature water begins to boil, you'd say, well, that's easy. It's 212 degrees Fahrenheit or 100 degrees Celsius. If I ask you how many sides a snowflake has, now you guys in Charleston may not see so many of those, but we see them where I am. It's always 6 sides, 6 points, 6 faces. And the reason for that is how the hydrogen and oxygen atoms are hooked together to form a molecule of water. These are settled science. Nobody debates them. Well, guess what? The fact that CO2 blocks long wavelength radiation is just as settled for 119 years and counting. When somebody tells you it's not settled science, they're wrong. They're either lying to you or they're ignorant. It is wrong. So from 1896 on up into the decades that followed, there were a lot of other discoveries that confirmed this greenhouse effect, a lot of other refinements to it, leading up to 1988 when the IPCC was formed, and also a man named Jim Hansen, who had worked for NOAA, testified before Congress and said, folks, we've got a problem. The atmosphere is starting to heat up. In 2001, the third IPCC report was published, and it stated baldly that global warming was unprecedented since the end of the last ice age, is very likely with highly damaging future impacts, possible severe surprises. It was the effective end of debate among all but a few scientists. 2001. 2008, climate scientists made this announcement. Even if all greenhouse gas emissions could be halted immediately, global warming would continue for millennia. So what we're putting up there today hasn't done all of its bad effects yet. It's going to take centuries and maybe millennia for us to feel it. If we stop polluting the atmosphere with carbon today, we would still increase the heating. Now the fifth assessment report that I mentioned earlier that came out in 2014 made this statement. Human influence has been detected in warming of the atmosphere and the ocean, in changes of the global water cycle, in reductions in snow and ice, in global mean sea level rise, and in changes in some climate extremes. They go on to say, this evidence for human influence has grown since AR4. It is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. And they define extremely likely as a term that's real important to them. It has a 95 to 100% confidence level. Think about that. 95 to 100% sure. And these are 1,300 scientists poring over thousands of reports. They even responded to 50,000 comments to this AR5 report. Some people try to act like that the IPCC is a big conspiracy. I don't know if you've heard that, but I've heard it, and it's laughable. How could 1,300 scientists reading 50,000 comments, maybe 30,000 peer-reviewed reports, manage to put together a report that takes 2 or 3 years to write and have some big secret that they're hiding something or that they're twisting the facts. I remember in my lifetime there was a president named Richard Nixon, and Richard Nixon and some of his guys decided to look in on what the Democratic National Committee was doing in regard to the upcoming election. And some people broke in, and the place was called Watergate. I'm sure you've read about it. There were maybe a dozen people who knew what was going on. Well, guess what? One of those dozen decided to disclose that to some reporters named Woodward and Bernstein, and they named him Deep Throat, and they began telling these reporters what was going on. And the rest, as they say, is history. It brought down a presidency. 12 people couldn't keep a secret. About 12 or 14 years ago, I was involved in a bank board, and we started a little local community bank up here, and we decided we were going to sell it. So a bigger bank wanted to buy it. That's typically what happens. And there were 12 of us on the board and 3 other officers in our board meeting on a certain day where we had to vote to approve or not approve the offer. And we voted to approve it. On the same day, about 60 miles away, another bank board met and decided whether to approve or disapprove the offer to buy us. They also approved it. So on one day, back in 2002, I think it was, a total of 30 people knew a secret. And the secret was that one bank was going to be acquired by another. Now, banks are usually listed on the stock market. So when you start doing stuff like that on a publicly listed company, the rules of keeping it secret are very strict. You are not allowed to let the public know this. It becomes inside information until it's been properly released through the financial markets. So what happens when the 15 here in Boone and the 15 in that other town go home? They tell their spouses. So now there's 30 people in Boone and 30 people in the other town that know this bank deal is going to happen. By the next day, 24 hours later, everybody's sworn to secrecy. 24 hours later, our phone was ringing off the hook and everybody said, "Hey, I heard there's going to be a bank merger." And so 30 people, ultimately 60 people couldn't keep a secret. And then I'll make one final example of how hard it is to keep a secret. There was another president, his name was Bill Clinton, and he was known as a skirt chaser, I guess. And one of the skirts he chased was this lovely young lady whose name was Monica Lewinsky. She was an intern. So Bill Clinton and Monica Lewinsky had somewhat of an affair, and of course it needed to be kept a secret. Well, she just told one person. How do you keep news like that secret? So she just told her best friend, Linda Tripp. Well, Linda Tripp couldn't keep that a secret. And all of a sudden it got into the news and it almost brought down another president. The point I'm making is that when somebody tells you the IPCC is a rigged process by a bunch of people who have a conspiracy to slant the news and make it the way they want it, it's wrong. They're lying to you and they're just wrong. Don't believe a word of it. Okay, so what do we know about climate change? Actually, what do we know that makes us think climate change is real? I'm going to give you a few points. The month of April 2015, last month, was the 350th month in a row that the average temperature for that month exceeded the 100-year average for that month in the 20th century. Now, did you get that? The month of April 2015 had an average temperature. I don't know what it was. But that temperature was higher than the average for all the Aprils for the 100 years of the 20th century. It's been almost 30 years since we've had a month whose average temperature for that month was lower than its month in the prior 100 years. So if somebody tells you that it was cold in Indianapolis last year or that Washington, D.C. had a lot of snow, those are meaningless comments. But when somebody tells you there's a 30-year trend, an unbroken trend in increasing temperatures, now you can start to place some weight on that. That is actually an evidence of climate change, whereas any one event is just weather. So remember that. Also, sea level rise. Global sea level rose about 17 centimeters, which is about 6.7 inches in the last century. The rate in the last decade, however, is nearly double that of the entire last century. Global temperatures are going up. All three major global surface temperature reconstructions show that Earth has warmed since 1880. Most of this warming has occurred since the 1970s, with the 20 warmest years having occurred since 1981, and with all 10 of the warmest years occurring in the past 12 years. So 10 of the warmest years since 1880 have occurred in the last 12 years. I see a pattern here. And even though the 2000s witnessed a solar output decline resulting in an unusually deep solar minimum in 2007 through 2009, surface temperatures continue to increase. So when somebody says, well, it's a natural solar cycle, take them to task over that and say, yeah, there are natural solar cycles. And if that was the only thing at work, we would be cooling, not warming. The warming has come in spite of a cooling solar cycle. And if anybody doubts that, have them call me and I can show them where the facts are. The oceans have absorbed much of the increased heat, with the top 700 meters, or about 2,300 feet of ocean, showing a warming of 0.3 degrees Fahrenheit since 1969. The Greenland and Arctic ice sheets and Antarctic ice sheets have decreased in mass greatly. Data from NASA's Gravity Recovery and Climate Experiments show Greenland lost 150 to 250 cubic kilometers, or 36 to 60 cubic miles, of ice per year between 2002 and 2006, while Antarctica lost about 36 cubic miles of ice per year between 2002 and 2005. Also, the Arctic sea ice has been declining not only in coverage but also in thickness over the last few decades. And the minimum ice cover every year in the Arctic is in September, and the last few Septembers have set some records for the least amount of ice cover. It's not going to be long until the Arctic will be ice-free in the summer. Glaciers are retreating almost everywhere in the world, including the Alps, the Himalayas, the Andes, the Rockies, Alaska, and Africa. Over 90% of all glaciers on the planet are shrinking. I've been to Glacier National Park. There are almost no glaciers in Glacier National Park. If you want to see a glacier in Glacier National Park, you need to get on out there. The number of extreme high temperature events in the United States has been increasing, while the number of record low temperatures has been decreasing since 1950. And the U.S. has also witnessed increasing numbers of intense rainfall events. 4 or 5 years ago, there was a 1,000-year flood over in Nashville. There was just a flood in Houston in proportions that they had never seen before. I don't know if it's a 500-year flood or maybe a 1,000-year flood, but these things are going to become more prevalent. Ocean acidification. Since the beginning of the Industrial Revolution, the acidity of surface ocean waters has increased by about 30%. This is a result of humans emitting more carbon dioxide in the atmosphere, and it gets absorbed into the ocean, like carbonic acid. The amount of carbon dioxide absorbed by the upper layer of the oceans is increasing by about 2 billion tons per year. Now you say, well, what difference does the acidification of the ocean make? Well, I'll give you one small example. There's some little critters in the ocean called phytoplankton. And phytoplankton, I'm sure you know this, it's a little organism that uses photosynthesis to make energy. And so what it does to do photosynthesis, if you haven't learned this, you will, it takes up carbon dioxide and it gives off oxygen. And when these little critters die, they settle to the bottom of the ocean and therefore become a carbon sink. So it's been a really good thing that the phytoplankton do what they do. And the other good thing they do is they give off oxygen. The oceans give off more oxygen than all the tropical rainforests put together. So as we acidify the oceans, we're slowly but surely killing off the phytoplankton. We're also killing off the coral reefs. If you know about coral reefs, you know that coral is a little coral polyp, which I guess is an animal, and it has this relationship with an algae, and I'm not sure if you say alga or algae, you'd know that. And the algae produces energy that the coral polyp uses. So when the oceans get too warm or they get too acidic and the algae dies, guess what happens? The reef becomes bleached out white. When you see these bleached reefs, it's because all the algae's been killed out. So we do that. These are not trifling things we're doing. This is a big source of oxygen. This is a big source of carbon storage, and we're ruining it. We're messing it up as fast as we can. And so on. I guess that's enough bad news about what's happening as a result of climate change. Well, there is one other thing. There's the migration of disease vectors, and that's the whole purpose of talking about the topic today. Other likely outcomes, there's going to be bigger hurricanes and cyclones. We've started seeing cyclones around the world that they call mega cyclones or whatever. More and stronger tornadoes. Melting glaciers, we just talked about that. Rising sea levels. More snow in some places and less snow in others. More rain in some places and more drought in others. Ask California about that. Species extinction, I want to talk about that a little bit. And then, of course, migration of disease vectors, which is the whole basis of this study of epidemiology. So now that I've gotten all this off my chest about climate change, if you have any doubt about how I feel about it, ask me. But you shouldn't doubt it by now. What does that have to do with disease vectors? Well, almost all tropical diseases that we're starting to see in the United States and places north of the tropics are carried by things like mosquitoes. And mosquitoes have to survive, and they have to survive winters as well as summers. They love the summers, and the question is, are the winters so cold that everything about the mosquito freezes? And in places north like the United States, as a rule, we haven't had much of a mosquito problem, and certainly not the kind that carry these deadly diseases. But guess what? The tropical regions are moving northward because of the increased heating. It doesn't take a rocket scientist to realize the mosquitoes will come along for the ride. And let's just talk about the northward movement of warm places in general, and then I'll get back to the tropical disease vectors. So a study that was done by NOAA indicates that tropical climate patterns may have expanded by up to 4.5 degrees of latitude in the northern hemisphere just over the last 25 years. 4.5 degrees is a lot. Also, this is the thing, I'm working on a book, and here's something I wrote in one of the chapters having to do with extinction and climatic disruption. Here's a study I referenced that said overall species will need to move about 2/5 a kilometer per year northward to keep up with changing conditions. That's 10 to 100 times faster than they've ever had to move before to cope with changing climates. Another article from 2011 said that such movement is going to have to amount to about a mile a year, saying about 2,000 species examined are moving away from the equator at an average rate of more than 15 feet per day. Think about that. You say, well, that's not much, but it is if you're a little lizard, or it is if you're a worm or a spider or a snake. That's a lot, 15 feet a day. Also, the species who can't move northward are moving uphill on mountains at the rate of about 4 feet a year in elevation change to a higher elevation. And here's some findings from another study. The British common butterfly moved 135 miles in 21 years. The British spider Silamoptopus has moved its home range more than 200 miles north, averaging 8 miles a year. Think about that. In Borneo, certain moth has shifted 220 feet upward on Mount Kinabalu. Also, the pika out west in the Rocky Mountains didn't go higher than 7,800 feet in elevation in 1900. Now they're going, in 2004, they were seen at 9,500 feet in elevation. So what does it mean? Do these animals have a political agenda? Do these animals make sound bites for the 6 o'clock news? Do they try to appeal to their political base? No. Nature doesn't waste resources, which means that animals do what comes naturally and they don't do anything they don't have to do. There are no hidden agendas or nefarious intent or ideology. They're not faking this for some agenda. So think about that a minute. The data shows that the tropical zones are moving northward, and it shows that animals which are affected by climate, which virtually all animals are moving northward at rapid rates. And so without any doubt, things like mosquitoes will come along for the ride as well. So the first annual frost in an area tends to kill off mosquitoes, ticks, and flies. But warmer temperatures are delaying the frost, and they're pushing the frost line farther north. It creates the potential for year-round disease transmissions in some parts of the country. Let's talk about mosquitoes in general. Temperature, precipitation, and humidity are critical to mosquito survival, reproduction, and development. Mosquitoes capable of carrying and transmitting diseases like dengue fever, for example, now live in at least 28 states. Have you ever heard of dengue fever? I hadn't. It's a tropical disease, and as the temperatures increase and the rainfall patterns change and summers become longer, these insects can remain active for longer seasons and in wider areas, greatly increasing the risk for people who live there. I'll bet everybody's heard about West Nile virus. I remember when that thing came onto the scene. This was 1999 was documented. By 2005, over 16,000 cases of West Nile virus infection have been reported. Warmer temperatures, heavy rainfall, high humidity have reportedly increased the rate of human infection. And this is pretty nasty stuff. Symptoms include fever, headache, body aches, skin rash, swollen lip glands. Severe symptoms may include stiff neck, sleepiness, disorientation, coma, tremors, convulsions, and paralysis. You don't want to mess with West Nile virus. And the mosquito that's indicted in this is called the Culex pipiens mosquito. Also, let's talk about malaria. Malaria is one of the biggest sources of death around the world. Malaria was eliminated from the United States in the early 1950s. By the way, I think one reason malaria was eliminated in the 1950s was from the widespread use of something called DDT. Well, that didn't work out very good either, but it did wipe out the mosquitoes. Now there's about 1,500 to 2,000 cases of malaria reported every year in the U.S., and most of it is from recent travelers who have been in areas that have malaria mosquitoes. It's the Anopheles mosquito, and I imagine you've studied this. So outbreaks of malaria and the reinfestation of Anopheles mosquitoes in the United States is almost certainly going to happen now that the warmer temperatures are moving farther to the north. Dengue fever. It's caused by one of 4 related viruses also transmitted by mosquitoes. It's called, otherwise known as breakbone fever, characterized by high fever, headaches, bone and joint aches, and a rash. Recurrent infection can lead to bleeding, seizures, and death. It's some more bad stuff. In 2009, dengue emerged in South Florida and infected more than 60 people. That's the first outbreak since 1934. It's back. Another one, chikungunya, may also set up shop in the United States. This disease's name literally means that which bends up. And it's an East African language word, since the afflicted are often contorted from joint pain. This disease spreads through mosquito, particularly the Asian tiger mosquito, an invasive species that is expanding from the southeastern United States and may reach as far north as New York. Okay, so time to wrap this up. We've talked about epidemiology and we've tried to define that. We've talked about climate change and defined that. I mentioned 3 ways to arrive at truths, especially when you're looking at this topic. And of course the first was critical thinking. The second is our good old friend, the scientific method. And of course when it comes to climate change, the Intergovernmental Panel on Climate Change, and their 5 reports, especially this last one called AR5. It talked about a paradigm, which is a term hopefully you'll incorporate into your vocabulary, and we talked about the commercial paradigm that's been in place for about the last 200 years and why part of that paradigm has always been wrong, the part about burning fossil fuels having no downside. What we know, and we also went over a short timeline having to do with climate change and realizing that we've known for 119 years and counting that carbon dioxide molecule blocks long wavelength radiation from getting through and therefore creates a greenhouse effect. We've talked about outcomes that are already apparent from climate change, including the migration of tropical disease vectors such as mosquitoes, which was, I guess, the basic reason for this talk. What I haven't talked about, just in the interest of time, a very, very, very important development is that in the Arctic regions of the world, there is a huge amount of methane locked up in frozen organic matter there that was put away tens of thousands of years ago. And as the permafrost is melting to a deeper and deeper level every year, that methane is coming out of the ground, bubbling up. And what's interesting is that methane, as a heat-trapping gas, is 86 times more potent than carbon dioxide in the first 20 years after it's released. And if you take a 100-year time frame, it's 32 times more potent as a greenhouse gas. And that's bad news enough, but the really bad news is there are trillions of cubic feet of methane that we're releasing because we are putting the carbon dioxide in the air. So that's what's called a positive feedback. Maybe I'll do another talk someday and we'll talk just about methane. But here's what's coming. These things have already started, but they're going to be accelerated and become worse. Sea level rise. And you say, well, that's not going to bother me, but yes, it will bother lots of things, including water tables and where people live. Mass extinction, we're now undergoing the 6th great extinction in the history of the planet, and it's caused by humans. Glacier melt, we talked about that. One outcome of that is that the meltwater streams have more water volume now than they ever did. And guess what's happening in South America? The people who live there say, oh, happy day, we've got more water. So they're expanding their agriculture and their populations are growing. But guess what? That water is not going to last once the glaciers are melted. That water's going to reduce and eventually go away. It's a terrible outcome. There are heat waves that are more apparent now. There was a deadly heat wave back in Chicago 10 or 15 years ago. There's a heat wave going on today as I speak about this in India, and 1,400 people have already died from the heat. You can see pictures of where the pavement is melting. The disease migration, we always think about America, and yes, I talked about what's happening here in the United States, but this same effect is happening all over the world. There are now climate refugees where people are being displaced because of droughts or because of rising sea level. There's a thing called heat stress on the boreal forests. Boreal is a term, of course, that means northern. So if you look at the northern forests in Canada and over in Siberia, the top part of Asia, these hardwood forests, which are wonderful carbon sinks, are now under heat stress, making them vulnerable to beetle infestation. So instead of a tree becoming a carbon sink, these trees are going to become carbon emitters. So the bad news gets worse. And of course, death of the ocean ecosystems, and we're already seeing that because of acidification and heat. So the problems are getting worse. These problems have been growing for generations. My generation, unfortunately, hasn't done anything to try to fix this because we're dysfunctional in our Congress. These problems are going to be yours to solve and your children's to solve, and I'm really sorry that it's this bad. But you just simply have to pay attention to this. Be aware of this. Take this seriously. This is not trifling. Use critical thinking. Rely on science for your data, not some ideological biased person who's telling you what they want you to believe because that's what he wants to believe. You've got to convince our leaders to begin leading on this. And with all that said, I wish you good luck. And I'm going to do all I can to help before I'm gone. Thanks a lot.